In the last class, we discussed two-dimensional experiments, especially correlated experiments, direct correlation like HSQC, TOCSY, heteronuclear correlation, HETCOR experiment like that. And I said HSQC establishes correlation among immediately coupled neighbors. TOCSY gives us the correlation among all the couples in a single experiment. Heteronuclear correlation establishes connectivity among the heteronuclei, and heteronuclear HETCOR experiment establishes one bond connectivity. CLOC is a long range correlation, establishes connectivity among the carbons and protons which are separated by 2 bonds or 3 bonds, etc. And we discussed about various advantages and disadvantages of all these experiments, the way they are represented. I said HSQC is symmetric with respect to diagonal, TOCSY is symmetric with respect to diagonal, and the cross peaks are always symmetric. Whereas in the heteronuclear correlation experiment, they are not symmetric. One has a large chemical shift along carbon 13, let us say, has a different chemical shift range compared to proton. It can never be symmetric. Okay? And there is no diagonal. Important, please remember, in the heteronuclear correlation experiments, there is no diagonal, and there are and there is no symmetry. They are all different spectral widths and both F1 F2 dimensions. And I said direct detection takes enormous amount of time. As a consequence, inverse detection can be done. The inverse detection is done in an intelligent way. Take the proton magnetization, give it a carbon or nitrogen that dilute spins or low abundant spin, take it back and detect proton. In the process, there is coherence transfer between these two, and you can establish connectivity, that especially the chemical shift connectivity among directly bonded heteronuclei or even remotely bonded. And they are accordingly called HSQC, HMBC, HMQC experiments. HSQC establishes direct connectivity among heteronuclei between two heteronuclei which are one bond coupled. More than 2 or 3 bond coupled, we use HMBC experiment. So right now today what we will do is we will start discussing about HSQC spectra, how we get and everything. Quickly go through one simple interpretation, etc. Because this time is running short, what we will do is we will see HSQC and HMBC. HMQC is identical, there is a small subtle difference which I do not want to touch upon. Okay. Before going into HSQC, I want to tell you something about satellites in proton spectrum. Why I am bringing satellites here? Very important to understand coupled and decoupled HSQC. Let us say I have CHCl3 peak. If you look at the proton, you get only a single peak. If you look at the carbon 13, what you will get? You will get 2 peaks, doublet. How is it possible? Interactions in NMR are always mutual. That is what I said. If proton is coupled to carbon, carbon is also coupled to proton. Both are true. Why in proton you get a single, whereas you get doublet in carbon? Here this proton is coupled to carbon, JCH. But you are directly detecting carbon 13. In this case, you are detecting proton which is attached to 12 carbon. See, 99% abundance is 12 carbon. So you will not see any coupling. Carbon 12 has zero magnetic moment. Spin is 0. Whereas 1%, where is 1% carbon? 1% of the molecule has carbon 13, carbon is carbon 13 state. That will give rise to coupling. So in the proton spectrum, you will see large peak which coming because of 99 molecules which are carbon 12 in the carbon is carbon 12 state, one molecule is in carbon 13 state, and this gives us a doublet which is exactly equal to doublet in the carbon 13 spectrum, and this intensity is 1% compared to the big peak. That is why they are called satellites. So the satellite spectrum is very important to understand, because we will see when you go to the HSQC how they are useful. So if you take the CHCl3 spectrum, 99% of the signal intensity is coming because of carbon 12 attached to proton, and only 1% is for carbon 13 attached, and that is further split into a doublet because of coupling with carbon 13, the intensity is 0.5%. Okay. Now HSQC and HMQC, with this we will go to further. They correlate chemical shifts of proton and chemical shifts of the directly bonded carbon, HSQC and HMQC. Both utilizes one bond coupling. A small subtle difference is there. Both HSQC and HMQC provide the identical information with small difference, especially signal to noise ratio and in HH coupling coming in one of the experiments. We will not discuss that. Whereas on the other hand, HMBC, heteronuclear multiple bond correlation, this experiment differs from HSQC or HSQC in that it establishes connectivity among between heteronuclei which are separated by 2 or 3 bonds. In the one bond, J coupling is very large, but let us say carbon and proton, one bond J coupling more than 150 hertz, 150 to 250, whereas 2 bond or 3 bond is only 2 to 15 hertz. So HMBC can be utilized to establish the correlation between 2 heteronuclei that are separated by 2 bonds or 3 bonds. They are called, that is called HMBC type experiment, HMBC experiment. So cross peaks are between protons and carbons that are 2 or 3 bonds away in HMBC. Cross peaks are between directly bonded proton and carbon in HSQC. But now what you may ask me a question in HMBC, what will happen to this one bond peaks? One bond, there is a, see if I look for the molecule like this and there is a proton here, there is a direct one bond correlation that also gives cross peak and this also gives cross peak. Then what will happen to this direct, which anyway we are getting from HSQC? But what we do is in HMBC we suppress this one. We detect only correlation between long range correlation over 2 or 3 bonds. Direct one bond correlation peaks are suppressed. This is a basic HSQC pulse sequence. Here it is like an inept sequence. If you remember inept what we discussed, this is an inept sequence where the polarization transfer takes place from proton to carbon here and they are allowed to evolve here. Of course, we have is a spin-loco like sequence here and then reverse transfer is done here. Magnetization which is taken from proton to carbon and from carbon to proton it goes back. It comes from magnetization, transfer goes like this from proton, here it comes to carbon, then it goes to proton again and we detect proton while decoupling carbon 13. This is the way magnetization get transferred in HSQC type experiment. Rest of the things are subtle details for experimentalists, you do not worry. In both HSQC, HSC mechanism, polarization transfer is identical. HMQC, HSQC, all are identical. What we do is, we take I spin, do the polarization transfer using inept to S spin, allow it to evolve during time T1, then do the reverse polarization using reverse inept, give the magnetization from carbon to proton back and start detecting proton during the detection period. This is the basic pathway is adapted in HSQC and HMQC experiments. So now let us start with these experiments can be both coupled HSQC, coupled HMBC, decoupled HSQC and decoupled HMBC. You can see that carbon proton are coupled in the 2D experiment and they are also decoupled. When they are decoupled it is very easy, you can directly get one peak is there, go vertically or horizontally both, you can get identify chemical shifts of proton and carbon. But if it is coupled version, there is multiplicity also. You can do that, you can get information like that also. See, take a molecule like this. Now you please understand carbon, that is why I introduced satellites, carbon 13 has 1% abundance. Now if in a molecule like this, always you see there is 1% of the molecule here which is carbon A in carbon 13, carbon B is in carbon 12, some portion of the molecule, and in some portion of the molecule carbon B is in carbon 13 state and carbon A is in carbon 12. So this is 1%, this is 1%. So probability, and when I explained the carbon 13 you remember I said these are 2 different isotopomers and you get the superposition of spectrum from 2 isotopomers in carbon 13 NMR, that is what I said. So this is what let us assume with this. Now we will see coupled HSQC spectrum. In the HSQC spectrum what will happen is there is a cross peak in the F1 dimension, this is HSQC spectrum, there is a cross peak in the, this is F1 dimension, this is F2. F1 dimension at A, at F1 is let us say carbon A which is directly bonded to carbon B. So there is a, that is you may see the spectrum, we will see that instead of drawing in the next slide it will come. HSQC gives for peak at F1 for carbon B and it correlates for F and it couples to carbon and proton in the F2 dimension, which is a doublet because of carbon Hb coupling. See, look at this molecule. In the F1 dimension, you are going to have a peak here. Let us say there is a peak here. But in the F2 dimension, actually it is not a single peak. If you, in this axis, it is only one peak. But in this axis, it is two peaks. The doublet comes because of the coupling of carbon with proton. In natural abundance carbon 13, it is okay, directly observed. In the proton dimension, how it will come? It will come as satellites. That is why I introduced satellites here. Okay. So, look at the spectrum of this molecule. Doublet is seen in the proton resonance. This is the carbon dimension, this is the proton dimension. In the proton dimension, you get a single peak that correspond to carbon attached to 12 carbon, strong peak. But there are two chota peaks here, these are satellites. These satellites are coming because of coupling of carbon to proton, carbon 13 to proton, which splits into a doublet. Similarly, for the Hb proton, there is a peak here exactly at the center, correspond to carbon 12 attached to proton. Whereas in the F2 dimension here, in this dimension, you get a doublet. This is corresponding to coupling between carbon and proton, Hb. Carbon attached to proton attached to carbon B is going to split this into a doublet. Here, proton attached to carbon A split this into a doublet. So, in the coupled HSQC, you will see the coupling pattern in the F2 dimension and a single peak for each carbon in the F1 dimension. Of course, you can interchange the dimension also, that there are several experiments like that. I am taking just simple broad experiment which is commonly employed. So, center of the doublet here correspond to the chemical sheet of A, this is center of it correspond to chemical sheet of carbon B. So, doublets are nothing but carbon 13 satellites observed in the proton spectrum. Remember, that is what I explained to you, the satellite in the proton spectrum. Now, in the case of HMBC, something more interesting will happen. Here it is a long 2 bond correlation, 3 bond correlation. Now, this carbon correlates to proton here, Ca. So, carbon B here has a peak here in this dimension correspond to carbon chemical shift, but its correlation is with this is carbon B. So, this its correlation for the carbon B is with proton A, not with proton B. Remember, here in the previous example, the correlation was directly bonded proton, but here in this case it is for remotely bonded. This is carbon A, you can see this is the chemical sheet of carbon A, whereas if you go vertically up, it is correlated to proton B. Where is proton B? It is here. So, this is the 2 bond correlation. This is HMBC. HMBC gives correlation to the next proton attached to next carbon, not for directly bonded proton. Similarly, look at this carbon B. You go vertically like this, go horizontally like this, you get carbon 13 chemical sheet of carbon B. But if you go vertically up, you do not get carbon A, you get you do not get carbon B, but you get carbon A. See here, carbon B gives correlation to carbon A gives correlation to carbon B. So, you understand. Here, the very interesting thing you should observe when you are looking at the heteronuclei here. This is a heteronuclear correlation is going on here. Let me just quickly say, because this is very important experiment which every time people will adapt, use carbon chemical shift of carbon B in this direction, carbon 13 chemical shift. In this dimension you will get proton chemical shift, but it is not proton B, proton A. Similarly, here carbon 13 which is carbon A, this gives carbon A chemical shift. If you go vertically up, you do not get carbon A, you do not get proton A, you get proton B chemical shift. That is the advantage here. So, it gives multiple bond correlation. You may ask me what will happen if I keep on increasing the length of the molecule. Now, I will bring CH proton. Another interesting thing happened. Here this proton to this proton coupling was not there. It was practically very small. Here these 2 protons can couple to this. Then this CH2 proton couple to this, it will become a triplet. When this will couple to this, it will become a doublet. Similarly, this will couple to this, it will be a doublet. This will couple to this, it will be a doublet. All those things are known. Okay, that is what we discussed. So, now HA is a triplet because of CH2 protons, and The 1H NMR spectrum, what you are going to get in the satellite? Carbon directly coupled to this proton. Okay, let us consider this carbon. This carbon directly coupled to this proton. In the HSQC, it will be a doublet. But now this proton is coupled to this, it will be a triplet. Satellite will give rise to proton couplings. Remember the previous course, we discussed about the satellite analysis, how to extract the coupling among equivalents, means everything we discussed. So here the multiplicity pattern is seen in the satellites. It is because of the coupling of proton with proton. This doublet separation is due to coupling between carbon and proton, but the multiplicity in the satellites is because of coupling between protons. Here coupling between proton and carbon, it is coupling between protons, and this is C12 attached, this is C13 attached satellite. So this is what it is. Similarly, same thing if you look at CB will be a doublet because of this satellite, and each line of the satellite will be a doublet because of coupling with this proton. Okay, very interesting will happen. Now if you want to correlate for the long HMBC, what will happen? We will come to that later. But please remember, in the satellite spectrum, satellite you can see the coupling or the next proton, which the carbon which is attached to the next, the directly bonded carbon is there, the proton which is attached to the next carbon, that will couple to this proton. So 2 bond coupling or 3 bond couplings can also be seen. Those proton couplings are seen in the satellite spectrum. Okay. Now coupled HSQC with proton coupling, let us see how the spectrum comes. Look at it, this is what it is. This is now carbon 13, this is carbon 13A, go along this axis, this is carbon 13 chemical sheet of Ca. But this is F1 axis. In the F2 axis, what is happening is, okay, in this dimension you have only one chemical shift along this, but in this dimension you have, see, 2 here. This is a triplet, this is a triplet. Exactly at the center of this correspond to chemical sheet of proton A. But each of these satellites you see is a triplet. Why they are triplet? This carbon is a doublet here because of this large coupling, and each line of the doublet is a triplet because of coupling with 2 protons. As a consequence, the satellite spectrum is a triplet. Each satellite is a triplet. You understand? Now we go back to this carbon B. Carbon B is very easy to understand again, is very simple. Look at this carbon B. If you look at this carbon B, now this is the F1 axis, you have only one chemical shift for this. Go along this axis, you will get carbon 13 chemical shift, F1 axis. But now in the F2 axis we have 4 peaks, doublet here and doublet here. Center of this exactly correspond to chemical sheet of proton. Why these two are doublets? These two are satellites. 1 bond coupling with carbon gives rise to this separation, and each line of this satellite is a doublet because of its coupling with neighboring proton. This is how coupled HSQC works. Okay. This is because of 1 bond JCA HA, and this separation correspond to 1 bond, not 1 bond, it is actually 2 bond HA H2. Similarly here also 1 bond JB here, 2 bond HBCH here. This is a 2 bond coupling. So now what will happen to HMBC? That is something interesting. HMBC, what it does is, this carbon A is the chemical sheet of carbon A along this axis, but it is giving correlation to HB. So carbon A is giving correlation to HB here. This HB is coupled to this proton and it is a doublet. So again what you would saw the doublet here among B, you are going to see that among at the site of for the carbon A you see this one, because it is correlation to HB. Carbon A is correlating to proton B, and it is going to be a doublet because of its adjacent proton. Similarly, carbon B correlates to proton A. Proton A, you see, this is carbon B chemical shift, this is carbon A, and each line of this carbon A of the satellite will be a triplet because of coupling with 2 protons. So you will see 2 triplets here overlapped. Since the long range couplings are smaller, it is not clearly visible. Okay, this is what is going to happen. So this is the thing you should remember. What is going to happen is, in the case of this one, see, this is the long range correlation here for this case. So long range correlation here, coupling of carbon A with proton, 2 satellites on either side. Also HV is coupled to CH proton. Each satellite peak is a doublet. That is for this one. Okay. Now for this one, long range correlation to HCB with proton HA, 2 satellites on either side because of CB, and then each of them is a triplet because of coupling with CH2 proton. This is the way you have to understand. Now simple analysis interpretation of a spectrum like this you can take, that proton coupled HSQC spectrum of ethyl acetate. Here we have CA3, CH2, CO. See, look at this one, CA3 here. This is not correlated to anything, only for this carbon. So this is CA3 carbon, and along at the center of this, if you go, you get these proton chemical shifts. On either side it is a triplet because this is actually this carbon, because this is coupled to these 2 protons. This is not this carbon CA3, this is this CA3. Because of that, this CA3, what is happening is, wait, let me erase it. Okay, because of this CA3, what I was telling, this is not this CA3, this CA3. This CA3, now it is coupled to this proton, so it is a triplet. On either side of the satellite, 1 bond coupling is there between this carbon and this CA3, and 2 bond proton coupling makes it a triplet. Now coming to this CH2, 1 bond coupling is here, this is CH coupling, and each of them is a quartet because it is coupled to CA3. When CH2 is coupled to CA3, it is a quartet. When CA3 is coupled to CH2, it is a triplet. That is what you are seeing, proton couplings. Whereas if you come to CO carbon, this is CA3 protons are directly coupled to this. This is not CO, I think this is CA3. CO cannot give because there is no direct attachment. You will see that only in the HMBC. This is CA3, this is coupled to this proton, and there is no proton coupling. Satellite is only 2 singlets. This is what it is. The same thing if you want to do, see the HMBC, this is this CA3, it is correlating to this proton. You see, this CA3 is correlated to CH2 proton. This is the CA3 carbon. Similarly, CH2 carbon correlating to CA3 proton, and each time you are going to give long range coupling, carbon correlation to this proton and this carbon correlation to this proton, but these proton couplings are seen. Similarly, like now if you come to this one, this is CO carbon, this can have a long range correlation with the CA3 protons or CH2 proton, either of them. Okay. So this is how HMBC has to be interpreted. Interpretation of HMBC is correlation to the next neighbor. So in 2D HSQC and HMQC spectra, the carbon 13 decoupling during acquisition of the FID removes multiplicity in the F1 FID. In the F2 dimension you will get singlet. So in fact in both the dimensions one can do the decoupling and you get a fully decoupled spectrum where direct correlation is possible. Look at this one. Here proton 5 is correlated to carbon 5. Here carbon 2 is correlated to proton 2. Here carbon 3 is correlated to proton 3. Carbon 4 is correlated to proton 4. This is a direct decoupled HSQC. So direct correlation, no couplings, no messy things are available here. Okay. Similarly, go to the HSQC spectrum of the same molecule which you saw earlier for TOCSY and TOCSY. Look at this. Here HMBC, HSQC spectrum. Of course, this is the expanded version we will see. This is a decoupled HMBC. This was HSQC in this thing. Now we will see HMBC. HSQC we already saw that. We should see the HMBC. Come to this proton 4 isolated. This proton 4 here, coming here, it comes to, it is correlating to carbon 5. So otherwise in this dimension carbon 5 is correlating to proton 4. Now this proton 5 should correlate to carbon 4. Look at this proton 5, this is correlating to proton 4. Very easy. Similarly, you can look at all other things. But interestingly, this carbon 1 has a correlation to 3, 4 and 2. It correlates into proton 2, proton 3 and proton 2 because there is a long range coupling for this. Like this, you can start analyzing the HMBC spectrum. Look at this one, carbon 2. Carbon 2 is correlating to, proton 2 is correlating to carbon 3. See, this proton 2 is correlating to carbon 3. Similarly, carbon 2 is correlated to this and carbon 3 is correlated to this. Very easily, the long range correlations can be very easily seen here. Look at this one, especially 2 and 3 I want to show you again, because very important to see the long range correlation is very sometimes it is very confusing to understand. So, let me repeat it. Proton carbon 3 is correlated to proton 2 long range. Here see proton 2 and this is carbon 3. Carbon 3. Proton 2, proton 3 here, now correlated to carbon 2 here. So, proton 2 is correlated to carbon 2 here. Like that, you can understand how easily you can start interpreting the HMBC spectrum. So, with this we have come to heteronuclear correlation experiment, but another very interesting experiment which I want to tell you. It is a very complex experiment. It is very time consuming experiment. It is called 2-dimensional inadequate. Inadequate stands for incredible natural abundance double quantum transfer experiment. It is called 2D inadequate experiment. Why do we use this? It is a correlation experiment, homonuclear correlation. Then you may ask me a question, homonuclear correlation already we saw 2 experiments, HSQC and TOCSY. Why are we bringing in another experiment? This correlates dilute spins or rare spins. What do you mean by that? Take for example CH3, CH2, OH. If I want to correlate this carbon to this carbon, it is not easy. It is very difficult. Only 1% of this is in carbon 13 and this is 1% in carbon 13 state. When we discuss carbon 13 we discuss these things. So, the probability of seeing both in carbon 13 is 1 in 10,000, very difficult, and we have to correlate that. When you are trying to correlate, there is a very big hurdle. What is the big hurdle we are getting? You are getting the interference on the dominant carbons that are not split by JCC. For example, each isotopomer, there are independent isotopomers. Remember, carbon 13 spectrum, as I said earlier, is a superposition of the spectrum for individual isotopomers, and carbon 13 coupling you are going to see from one of the isotopomer where both the carbons are in carbon 13 state, they will be split into J coupling, whereas individual carbons CH3, CH2, COH if you take, this is only one isotopomer, this is another isotopomer, and only this carbon 13 is dominant here, there is no coupling, and these peaks are much stronger compared to carbon 13 doublet, J split doublet. The biggest interference coming because of the dominant carbons from carbon 13 state, the one carbons which are single carbons which are not split by neighboring carbon. So, how do you eliminate that? We have to subtract that, only then we are going to get this long range correlation among dilute spins are possible. For this we have to use a double quantum filter. We can filter out all these things. So, when you use a double quantum filter, what will happen? All singlets will be removed. Remember what we discussed in the decoupled. Use a double quantum filter, all singlets, references, solvents, they all get eliminated. So, use double quantum, then all these carbon 13 peaks which are unsplit, which are not J coupled, will get eliminated. Then you get peaks only from 2 carbons which are coupled between themselves. Now, the question you may ask me is, why only double quantum? Why can't we use triple quantum, higher quantum? For that you should know, just now I said possibility of seeing 2 carbons in carbon 13 state is 1 in 10,000. If you have 10,000 molecules, only one molecule can have a possibility of both the carbons in carbon 13 state. and very remote probability when you have more carbons in simultaneously in the carbon 13 state. So, probability is only this 2 carbons in carbon 13 state. So, if I use double quantum, then I can filter out all single quantum and I can extract only these carbons, coupling among these carbons, very easy. So, that is why DQ filter is used and anything above that is not needed. Only DQ carbon 13 2 carbon 13 coupled at any given instant of time is useful. So, DQ maximum is enough to subtract this one. So, what we have to do in this experiment is initially we allow the DQ coherences associated with the coupled spins to evolve during a variable time, like our DQF. It is similar to our COSY and other DQF, COSY, we saw that. And then after some time we reconvert the this thing DQC into detectable single quantum. That is what we did in DQF COSY. Identical you can do here also, but it is for dilute spins. So, this is an inadequate sequence. This is like a sequence where homonuclear spin echo is there. It is makes excitation independent of the chemical shifts. So, you do not have to worry about chemical shift evolution here. They get refocused, homonuclear spin echo, chemical shift get refocused, but not J couplings. That is what we have been discussing. Whereas in the T1 dimension, the DQ evolution takes place after the next pulse is there. So, multiple quantum evolution takes place. Use a DQ filter from +2 to -1 using the phase cycling or gradients, and then choose this pathway. Convert, that means you are converting DQ coherence to single quantum coherence. Start detecting this while doing the decoupling. The advantage is you can continuously do the decoupling right from the beginning till the end. The thing is, advantage of that decoupling power is it not only decouples, gives rise to NOE enhancement. Please remember, during the NOE of the heteronuclear case I discussed, I said there is a possibility if you have the decoupling this, if you are decoupling proton and observe carbon, we saw that about 200% gain in the intensity we saw. There is an enhancement in the signal intensity because of NOE. So, the F1 F2 in the F1 dimension what happens is you get cross peak at the sum of 2 chemical shifts. We are looking for double quantum filter. Let us say there are 2 carbons, chemical shift is 1 and other is 2. In the direct dimension you get 2 peaks individually. In the double quantum dimension they come out the sum of the chemical shifts. Okay. F2 dimension gives 2 peaks at their corresponding chemical shift. While in the F1 dimension we get peaks at the sum of the chemical shifts. So, throughout the sequence carbon 13 proton decoupling is applied to get the NOE enhancement and also broadband decoupling of all carbons attached to all protons. So, now biggest thing you should understand is the 2 carbons couple the same double quantum frequency. The 2 carbons are there, they have 2 carbon chemical shift positions, but in the F1 dimension they share the same DQ frequency in the F1. Hence, you can make the correlation by horizontal traces. Go horizontally, find out which are the 2 which are coupled, giving rise to double quantum, and then go vertically up, you will see the correlation. So, carbon connectivity you can establish by sequence of horizontal, vertical, like a step ladder, keep on going horizontal and vertically, you will identify all the carbons which are coupled among themselves, which are there is a connectivity you can establish. Remember 2 coupled carbons, I am taking the example in the F2 dimension 2 individual chemical shifts, in the F1 dimension they come at the sum of the chemical shifts and go horizontally because 2 carbons share the common double quantum frequency. Identify 2 carbons along the F2 dimension, go vertically up, you will find out the coupled carbon, go vertically up from horizontally again another carbon which is coupled to that. Like that you can keep on going through this ladder, step by step ladder, horizontally, vertically, you will identify all the connectivity, you can establish all the connectivities. Again here, though it is homonuclear, remember there are no diagonals here, diagonal peaks are totally absent here, unlike COSY, TOCSY, etc. But since we are talking about double quantum, very interesting thing happen. I will show when you see the F2 dimension and F1 dimension. If you take draw exactly a line at the center of the doublets along the F2 dimension, you will get a diagonal, and that is called a pseudo diagonal where if you take the slope of it, for example, if it will like this, if you take a slope here f1 is equal to 2f2, slope is 2. That is why you are going to get a double quantum diagonal in this case. I will show you the spectrum of it, how it is, and each peak doublet correspond to AX like pattern. We will see the spectrum now. It is a simple molecule here. Now, how many carbons are there? 1, 2, 3 and 4. This is already identified for you, carbon 1, 2, 3 and 4. Normally, your idea is to identify the direct connectivities. Carbon 1 to 2, 2 to 3, 3 to 4, you have to identify carbon connectivity like proton connectivity we did. So, what we do is, I know this has been already identified, taken from the book of Timothy Claridge. Now, you look at this proton 1 which is identified, there is a doublet here. It shares the double quantum frequency with another proton, another carbon, go horizontally, you identify a doublet. These two form a AX spin system. So, AX spin means this is a doublet, this is a doublet. So, you got 2 doublets. So, this now this is 2 peaks for 2 corresponding carbons which are coupled, giving rise to AX pattern. Now, in the double quantum dimension there is a peak at some of the chemical shifts, go vertically up, you see one peak. Okay, this is 1 and 2 and 2 is here. Now, horizontally you go again this and thus becomes a doublet. This is a doublet, this is a doublet, again another AX spin system. 2 and 3 are coupled, forms an AX spin system. So, now if you go horizontally you can identify its coupled partner. Go vertically up you find another carbon, go vertically up horizontally again you find another carbon. Like this sequentially keep going like this, you can identify each of the carbons from their connectivities. So, this 2D connectivity always given in a magnitude mode for various reasons, and what I wanted to show you is 2D there is no diagonal, but there is a pseudo double quantum diagonal, and in the F2 dimension you get doublets corresponding to AX pattern, AX split doublets, go vertically up, identify its coupled neighbor, again go horizontally, again 2 spins, coupled spin system, 2 AX pattern, go vertically up and again like this you keep on going ladder wise, step by step, horizontal vertical, you can establish the connectivities of all the carbons connected among themselves. You can establish the carbon connectivity, that is the dilute spin connectivity. This is a very important experiment called 2D inadequate. There are variations of this again. So, all the 2D experiments which we discussed, number of variations are there, but what in this course I am giving is basic introduction, basic concept, basic idea how it works, basically how we utilize these things. For the improved versions you can go back to the literature and start reading all the books. So, with this my time is up, I am going to stop here, but I do not know whether I will be able to continue 2D or again in the next class, for the reason time is up and I have to cover multiple quantum, solid state NMR and various other things. Let me see how much time is going to be left. To, if possible I will come back to solid 2D again and cover Jresolved, and then possible NOC and ROSI I will cover if there is a time, if I will come back. Of course, Jresolved we discussed in the last course also in depth. It is very simple. It is only separation experiment where you get chemical shift in one direction and J coupling in other directions. So, NO is another experiment, it is a transient experiment. Of course, steady state we saw by selective decoupling of one of the irradiation of one of the peak and seeing the change in intensity by subtraction, that is a different experiment. But a transient NO we can do in the 2D way. I do not think I have time to cover so much now, but what we will do is we will wait for some till the end. Next class I will go to multiple quantum NMR, I will go to solid state NMR. Hopefully, if I left with some another half an hour, 1 hour slot, any half an hour slot if it is available, I will come back. Anyway, you already have all the information about 2D. I will just in one class I will discuss about other 2D experiments. So, 2D I will not continue further, I will stop it, we will go to MQT in the next class. Okay, thank you very much.